about test-driven machine learning. Thank you, Valerio.
Okay, thanks a lot for coming. Really appreciate it. This talk is intended to be an introductory one. I'm not very comfortable with this mic, so please tell me if you can't hear me. I was saying this talk is intended to be introductory, so I will tell you what is test-driven development and what is machine learning in very few slides. And I would start by asking you, please, 3 questions. How many of you are in machine learning or already know what machine learning is? Thanks a lot. Okay. And what about test-driven development? Okay, so great. And how many of you use scikit-learn for their machine learning code? Okay, so this is useful for the introductory part. Well, in Python we have a lot of machine learning tools. We have scikit, we have NumPy, SciPy, and then Python and Matplotlib for plotting, for data visualization. Actually, we have a lot of stuff also instead of these tools. In the next slides, in the rest of the talk, we will use scikit-learn, which is built on NumPy and SciPy, and IPython is always under the hood for notebooks or computation. And of course, Cython is another important component in the stack, technological stack of scikit-learn. Machine learning at a glance. What is machine learning? Machine learning is basically deals with statistical analysis and algorithms that are able to process data and to learn from data. If we would like to cast a definition about machine learning, we might say there are many definitions about machine learning actually, but this one is really interesting. It says that machine learning teaches machines how to carry out tasks by themselves. It is that simple. So that's just machine learning. So of course the machine here in the definitions, the machines here in definitions are meant to be algorithms. And the complexity comes with the details. That's the real problem about machine learning. So everything you need to set up your context, analyze your data, set up your data, sanitize your data. We will see something about this in the rest of the slides. So basically the essence of machine learning is we have a pattern in data, but we can't pin down the pattern mathematically, but we have data on it. So we might use the data, exploit the data to learn this pattern directly from them. This is called learning by examples in general. Machine learning and data analysis. Machine learning is about making predictions actually. I'm quite sure that many of you have also heard about stuff like data mining, which is not actually machine learning. The real difference is that data mining is about analyzing the data. That's why I called this data analysis. Machine learning is about making predictions. So analyze the data to forecast something. Okay, so to learn from the data and to learn some patterns from the data in order to derive some conclusions for future and unseen data. Data analysis, instead, is about analyzing the data we're currently working on. Okay, so this is basically the difference. And okay, this is the same slide. Sorry. Some examples of the machine learning. We have a classification problem. In this case, we have 2 different sets of points. These are colored red and blue. We want to learn a function from these data to classify these points. In particular, the classification function is this one, which is this is called the decision boundary. So the boundary that separates the data in 2 different classes in this case. Another well-known example is the clustering. So in this case, the problem is a little bit different, and we have all these data. All the data have the same color, and we want to generate groups from this data. In particular, this is the result after some clustering elaboration, some clustering processing. So we are able to identify the different groups composing the data. Actually, these two examples are examples of two different approaches to machine learning. The first one, classification problems, are also known as supervised learning models. The supervised learning refers to the fact that actually this is the quite standard machine learning pipeline. So if you're wondering what a machine learning algorithm is about, it is about almost this kind of pipeline processing. In the supervised learning model, we have data here. The first thing to do about the data is to represent the data in a format that is able to being processed by the algorithms. In this case, these are called feature vectors. Okay, so we are going to analyze, for instance, text, documents, images, source code, video processing data, audio files, whatever. We take the data and input, we change the data into a representation that is suitable for machine learning algorithm. So this is the first mandatory analysis step. Then we have labels, which is a characteristic of supervised learning models. So we have the data, we have the labels. The labels are the indication of, for instance, in case of classifications, on which are the classes associated to each data we are going to analyze. And this is called the training process. So we have a model here, we have a machine learning algorithm or a machine learning model. We define a function, a so-called learning function. We have data to train the learning function, and then after the training, so after this phase, the learning function, we have calculated the parameters of these functions. So we started by deciding which is a model. For instance, I don't know, in the example, the model was a linear model. So we have a decision boundary that is a linear function. And after the training, we learned the exact values of each parameter of that function. So by analyzing this data, and this model after the training is used to learn, so to make predictions for unseen and new data. Okay, this is this is the quite simple pipeline we always apply when doing some supervised learning model. The difference with the unsupervised learning, so in case of clustering, is that we don't have labels in the training. Okay, so we use the features of the data here to create some, in case of clustering, to create groups. In particular, we approach this problem by, for instance, comparing the distances among points in the space. So we create groups by collecting into the same groups points that are similar or not so distant in the space. In fact, the difference also lies here in the final prediction model. In the first case, we want to in the supervised learning setting, we want to learn the expected label. So here we have the labels to use for training, and afterwards we want to predict the label associated to new data. In the unsupervised learning approach, we want to estimate a likelihood or the cluster, the ID of the cluster where the data belongs to, or for instance, have a better representation of the data. Well, so what about Python? Python and data science in the last year is getting becoming more and more popular. Actually, there are some articles online that also tell us that Python is displacing R in some computation, some statistical analysis, and some data analysis approach. Indeed, we will have a talk here on Sunday, on tomorrow, about this kind of problem on how much Python could so far displace R, and in which cases. That's really interesting. So this is the top of the ranking of languages for data science, and Python is over there among Java, JavaScript, I don't know why, PHP, really don't know, Ruby, and this is CSS. Really doesn't make any sense actually, but MATLAB is over there, R, and other languages such as Fortran, really old-fashioned. That's it. Okay, there should be also Scala is over there. Actually, I think that these data are a bit outdated. Maybe Scala has some more has gained some more positions in the ranking because of, for instance, Spark. Oh, I don't know. These are reported in this article, but I don't know which one is the source. Indeed. Okay. Anyway, it's not so important. Oh yeah, it's really they're plotting considering the popularity here, and the it's quite difficult to read indeed. Let me check. Well, if you don't mind, we will check at the end of the talk. Yeah. Okay. Thank you. But anyway, this kind of ranking, in my opinion, are not so. Is just to make some snapshot of the situation. It's not important actually how much Python is distant from Java or Perl or R or MATLAB. Doesn't make any sense in my opinion. But anyway, indeed, this kind of considerations are what we heard about in this keynote, in the keynote this morning. Okay. Anyway, Python as one important feature among other languages is that Python benefits from the fact that it is a general purpose programming language, and in general it is used as a glue between different environments, different computational environments. Another consideration we may tell is that Python, with respect to MATLAB and R, has some tools that could be used for data science. In case of MATLAB, we have IPython, the great IPython project, which is now called Jupyter. Of course, NumPy, SciPy, and Matplotlib for visualization, and Pandas could be compared to the R because of, for instance, the data frame structure Pandas include and provides, which is basically a sort of Pythonic implementation of the R data frame. And also we have Cython, as said before, and then Anaconda and ThoughtCanopy, which are two Python distributions specifically devoted for data science and for scientific computations. And what about machine learning in Python? Well, we have a lot of libraries in Python. We have PyML, for instance, just to mention some of the most famous ones. We have scikit-learn, we have PyBrain or PyLearn2, the Shogun machine learning toolbox, PyML, SparkMLib, natural language toolkit, and machine learning MLPy. You may find a list. This is really interesting. You may find on GitHub at this link an awesome machine learning by Kevin Cobain. You may find a list of different machine learning tools and analysis tools in different languages. Okay, not only for Python, and it's being updated quite frequently indeed. The difference from these packages, SparkMLib is basically implemented in Scala. It tells porting in Python, but so far it is at a very early stage. The Python porting. The shotgun approach is different. The shotgun approach is behind, under the hood. Shotgun is implemented in C++ and is wrapped in Python. It has some advantages, of course, on the some efficient from the some efficiency point of view. And the other approach is Python packages like this one. These are all Python powered, but behind, under the hood, they differ from the fact that the approach they use to implement the different algorithms. For instance, an LTK, Natural Language Toolkit, is pure Python, so it's a bit slower than other approaches such as scikit-learn, which is implemented in NumPy and SciPy and Cython a lot. So why to choose scikit-learn for machine learning? Indeed, I would like to report the 6 reasons about why using scikit-learn by Ben Lorica, which is a prominent exponent of the worldwide data science community. Of course, for the commitment to the documentation and usability. In fact, one of the greatest thing about scikit-learn is its documentation, and it's supposed to be useful not only for data scientists but also for engineers who are willing to implement their code using scikit-learn. So in the general case, in theory, you may not be so familiar with any machine learning approach you're going to use. You may just put your code, and with few instructions you might have your machine learning code running out of the box. And that's pretty well documented with a lot of examples. The models are chosen and implemented by a dedicated team of experts. Actually, the stable contributors of scikit-learn includes some very experts in machine learning field and in software development. Covers most machine learning tasks. Actually, the philosophy behind the inclusion of some methods in the library is that if the method is quite famous and is quite useful to a large set of people, it will be included in the library. Then Python and PyData. It's an impressive set of Python data tools because scikit-learn is implemented in Python. The fifth reason is focus. Scikit-learn is a machine learning library. Its goal is to provide a set of common algorithms to Python users through a consistent interface. Actually, the interface of scikit-learn is very simple and trivial to use. And finally, scikit-learn scales to most data problems. And one of the things I like the most in scikit-learn is that it also includes it's a sort of battery included library. We will have a glimpse of this at the end of the talk. And if you would like to install scikit-learn, you just need to have NumPy, SciPy, and that's it, and matplotlib. So IPython is just to have some beneficial additional extra features. And if you use the Anaconda, for instance, Python distribution, you may have it already installed in your code. So the design philosophy, as I mentioned before, the design philosophy of scikit is to include all the batteries necessary for general purpose machine learning code. So this means that scikit-learn provides data and data sets, algorithms for machine learning, which are, for instance, classification, regression, or clustering, feature selection extraction algorithm, which are a sort of techniques to pre-process the data, and finally evaluation functions. These are really interesting for the topic of this talk. And all this stuff is battery included, so it's already included in the library. So the algorithm selection philosophy, as I mentioned before, is try to keep the core as light as possible, including well-known and largely used machine learning methods. And finally, this is the last slide I promised to about machine learning, about scikit, and this is very interesting because it provides a picture that you may leverage to understanding at a glance which are the features and the algorithms, the techniques provided by scikit-learn, and how you may choose the different techniques provided in the library. For instance, if you're going to analyze data that have less than 5 samples, please take more data. If you have more than 50 samples, then you have to decide, okay, well, you may need to predict a category. If yes, you have labeled data. Oh, great, okay, so go to classification. No labels, well, clustering. So it's pretty simple, okay? Of course, it's just for to introduce yourself into the different characteristics of the machine learning field. That's quite simple. Okay, so we ended up to the second part of the talk, and after the introduction to machine learning and scikit, the second part is dedicated to the test-driven development, so TDD. As you may expect, TDD is basically about testing. And I would like to tell you about TDD with few simple slides. TDD basically consists in a very clever iteration scheme. The first step of this scheme is the think step, which is the step number 0, I may say. You have to think about what we want the code to do. Okay. In few words, test-driven development means that you are driving your development, so the development of your features by testing. Okay, so this is the philosophy behind test-driven development, and this is usually applied to general-purpose software engineering. Okay, and in particular, test-driven development is one of the most famous practice of the agile methodologies, if you have already heard something about this. So step number 0 is think about what we want the code to do, and we may call this iterative scheme, iterative steps, the TDD mantra. So after thinking, we have to set up a walking skeleton. The walking skeleton is to, for instance, create a unit test. So we are going to have our test, which is completely nonsensical. So it's empty. Okay. So if we run this test, it doesn't make any sense indeed. So after setting up the skeleton, we run the test, and of course this test fails because say fail unless false. So we got an assertion error. Okay. Afterwards, so this is just an example. We want to create objects that can say whether two given dates match. Okay, this is our problem, and this is the driven example we're going to use in the next couple of slides. So this is the step number 0, think step. We want to create this object that given 2 dates, it provides matching for dates. So we start by writing our first test. Okay, so the walking skeleton. We supposed to have a date pattern, which is the class under test, the name of the class under test. So we put the dates, the data inside the class we're instantiating. Then we create a date and we call the testing method to check if the matches method of date pattern works properly. But please be aware that we didn't implemented any matches or date pattern method at all. Okay, because we started by creating the test first. So this test is meant to fail the first time. In fact, it fails. Okay. In particular, it says name error, global name date pattern is not defined. So it's quite controversial if TDD is really useful in software engineering. But the point is, if you would like to drive your development by tests, you should start by testing something that doesn't exist yet. And this is the case. Afterwards, the second step, right? The first one is called red bar, because you start by having a failing test. The second step is green bar, also known. Green bar, okay, write the code just to pass the test. Simple. So we have a class which is called date pattern. This class in its constructor gets the 3 parameter we want to handle. So year, month, and day. We have the matches method we're trying to input to test, and we implement the code just to pass the test. Okay? So we run the test again, and the test passes this time. Okay? And so far, the code implemented in date patterns just refers to the test we defined. Okay? So every feature we implement in the class on the test is driven by the tests themselves. Okay? Is that right? Okay, fine. And finally, the last step is also called the refactoring step. This is just an example, but the point here is if we develop a feature at a time using tests, we may end up in a code that is basically spaghetti code. So an important thing we should consider to do afterwards is to apply some refactoring. And what the tests are used for in the refactoring step. The tests are used to be sure that the refactoring applied to the code does not created additional bugs. So by running again the tests, we're pretty sure that everything implemented in the refactoring step didn't include also a bug, for instance. In this case, we may avoid applying these comparisons in one line. We may have 3 different methods, for instance. And we may, basically we here apply a so-called extract method refactoring technique. We created the 3 methods, and we had re-implemented the matches function, and we run again the test, and the test will pass again. So, thank you. So, no problems included. In Python, we have different frameworks for tests. We have unit test, just to mention the most famous ones. We have unit test, nose, PyTest, nose testing, and I'm sorry, this is not nose. It's my mistake. This is NumPy testing. This is interesting for data science. NumPy testing includes some additional assertion that are specifically devoted for arrays and ND types. In particular, we have assert array equal, so for instance, or assert almost array equal, okay, that are very useful in case we're testing NumPy code. And indeed, you may find a lot of testing tools in Python at this link. So basically, test-driven development is about, okay, you're programming the way completely wrong. Okay. So finally, what about test-driven development and machine learning? I would like to mention this book. This book is very interesting, and its greatest pros is that it's a great reference on the topic. Okay, but conversely, its cons is that examples on Ruby instead of Python. So first of all, no chance to present the code reported in the book in a Python conference. And the other problem is, I don't know Ruby. He does. So we need to tackle this problem by considering that, of course, no Ruby code will be presented in this talk. And anyway, what about test-driven development and scientific method? TDD is basically about hypothesizing, testing, and theorizing. And the scientific method goes through exactly the same approach. Trial and error, so come up with the hypothesis, test the hypothesis, and create a theory. Okay? So we might conclude that TDD is basically a subset of the scientific method. This is the point this is a statement that that book provides. And that's quite interesting. Indeed, TDD also provides, also makes logical propositions of validity, document the progresses, and in case of scientific method, this means writing the paper, the scientific paper. And finally, working feedback loops, which is really important in both test-driven development context and scientific methods. And if you would like to make a comparison between scientific method approach and the test-driven development, we may say that the necessary conditions, which are represented by the axioms in the scientific method, are represented by the pure functional testing in case of TDD. And the scientific sufficient conditions, so statistical hypothesis testing in case of scientific methods, could be replaced in case of TDD by unit and integration testing. So what about machine learning? Which are the risks of machine learning? So in other words, what we are willing to test, what we want to test. In case of machine learning, we may have to deal with, for instance, unstable data. So data which are unstable, so they've been provided by error, for instance, by programming faults, despite outlier reductions. So it's machine learning techniques to sanitize the data in some sense. We may end up with underfitting. So the underfitting means that the learning function we defined does not take into account enough information to accurately model the phenomenon we are going to learn. Or the opposite case is the overfitting. So the learning function does not generalize enough the phenomenon we're learning. And finally, unpredictable future. We don't actually know if our model is working or not during the computation. Thank you. So just to make an example, the difference for under and overfitting. You have this data, for instance, okay? In this case, and you're hypothesizing this model, the one represented in blue, okay? In this case, you're underfitting because you're just not considering any of these information, okay? And the other case, in the latter one, is overfitting because the model represented here is perfectly fitted through the training data, but does not generalize well, because these should be the right model. In this case, these should be a very well solution. The difference here in the polynomial model and the polynomial function is this degree 1, this is 15 degrees, so different 15. So we have 15 different features in our polynomial instead of 4, which is a very fair choice. I should skip some slides, so sorry about this. The point here is that scikit-learn already provides methods to apply the computation to the testing. Indeed, I would like to show this slide before. The point here is that how we may mitigate the different machine learning risks. In case of unstable data, we may apply sim testing, which means test the data just to verify the preconditions. In case of underfitting, we may apply cross-validation, which is a method that's used to scramble a bit the data we're using in training phase. The overfitting and the unpredictable feature, in case of overfitting, we may apply benchmark testing in case of the data we're training are working properly, but this is the most important one. Finally, is that unpredictable future is about tracking over time, precision and recall. And the point here I would like to state is that scikit-learn already provides methods and tools out of the box to apply this kind of computations. Okay. Indeed, I'm quite running out of time, so there will be no time for the example. I will provide the slides as soon as we will finish the talk. Basically, just to mention a few very quickly what the example is about. The example is about Iris dataset and SVM, which is a very popular machine learning method, which stands for support vector machine. And I reported a brief description of the datasets. Not really interesting, but finally, these are the tests, some examples of tests we may apply to test our machine learning model. I'm really sorry for not presenting you in details, but I will be more than happy to talk about this after the talk. So thank you very much.
Thank you very much, Valerio. Are there any questions?
Not really a question, but just to say that Python are not displacing R. What we have seen in the talk tomorrow, we show some numbers to you, is that is growing a group of polyglot data scientists. I don't like data scientist job title, but there is a huge amount of person and analysts using both and gluing the best from these two kingdoms for data analysis. Thank you.
That was the talk I was mentioning before. That this is going to be really interesting, and I'm quite. I agree with you, Joe, completely. So we will see what you're going to present on tomorrow. Any other questions?
So I wanted to ask if there's a specific tool for specific tests like pattern recognition, decision trees, or they all do the same, and also how much black box we can use them if we know enough about machine learning.
Okay, thanks for your question. Basically, my point is you may use classical testing tools in Python to test your algorithm, and basically, my opinion, the test-driven approach you may apply is related to one of the four points I mentioned before. So, indeed, you might, on the one hand, before running the learning algorithm, you might apply some preliminary testing just to make sure that your implementation, if you're not using a library, a stable library such as scikit is, just to be sure that your code is going to work properly. On the other hand, what you may apply is some testing using cross-validation to avoid underfitting, or apply precision and recall checking during the computation for to test that your model is learning properly. Okay, and actually, for the second question, I'm not aware of any testing tools specifically devoted for specific machine learning method, such as the random forest you were mentioning. But we may try to look at. In general, I think it's testing libraries quite enough.
Are there any other questions? Nope. Okay. Thank you very much, Valerio.
Just to say that I will publish the slides in a few minutes, so just to have the chance to take a look at the example at the end. So again, sorry for not being on time. Thank you.